Alright, so today we're talking about evaluating limits graphically. And we've done this back in lesson 7 where when you were first introduced to limits and basically you're looking at the y value. What's happening to the y value is x approaches a particular set point. Okay? So as x approaches like 2 or 4 or negative 3, you're looking at what's happening to the y's. Are they approaching a particular number? Are they approaching infinity? So on and so forth. So we are going to be using our calculators to find the limits. And if you don't have a graphing calculator at home or in your possession, then you're going to basically be using a table of values. And I'll show you how to do that in the first 2 examples. And that's what you'll do to evaluate your limit. So the reason why we are covering limits is because this is pre-calculus. And pre-calculus is a preview of calculus. And calculus centers around 2 fundamental problems. That's finding the equation of a line tangent to the graphical function at a point, and finding the area between the graphical function and the x-axis. Okay, that's what calculus really is about. 2 main topics: derivatives and integration. And the fundamental to the solution of each of these problems is the understanding of the concept of a limit. Now, if you recall back from lesson 7, that's when we first started talking about limits, is that the limit as x approaches c of a particular function equals L. L is some value. So it's basically asking you, as x approaches c, what is the y is going to equal? And that is what L is. And you can find this limit, again, by using a graph. So we're going to use our graphing calculator to do this, or making a table of values. And that's basically for those who don't have access to a graphing calculator. So we're going to jump just right on into it. We're going to estimate the limit as x approaches 2 of the function negative 3x plus 1 using a graph. Then we're going to support it by using a table of values. So if we notice, this is the graph of negative 3x plus 1. It is a line with a negative slope. And as x approaches 2, as x approaches this value right here, what's happening to the y's? And you should notice is that as x approaches 2, the y's are getting closer and closer and closer to negative 5. So the limit as x approaches 2 of negative 3x plus 1 is equal to negative 5. Now we can also do this using a table of values. Okay? We can also do this using a table of values. So we can also find this by using We can also find this by using a table of values. And to do that, all we do is actually take these x values that are really close to, like 1.9, 1.99, 1.999, on both sides. That's where the 2.001, 2.01, 2.1, and we just plug it into our function for x. And we actually figure out what these values are. Because we'll see that as x is approaching 2 from the left as well as from the right, it's going to approach negative 5, which is what we found out using our calculator. So plug those in and fill in this chart, okay? This is for those also who don't have a graphing calculator. This is what you're going to actually end up doing, okay? So hopefully you got these values when you plug them in. Now, when you plugged in 2, you actually ended up getting negative 5, which is what our limit was. But I didn't ask you what the limit was as x equals to. I asked you what happens as it approaches. So it's not really, and sometimes when you actually plug in the value that is approaching, you won't get what the actual answer is for the limit. You're looking at to the left and to the right of that particular x value. So I want you to do this one. You can either look at the graph on your calculator or you can complete the table, but I want you to tell me the limit as x approaches 3. So if you decide to look at the graph, hopefully you type the function in correctly and you got this, including parentheses around your numerator and denominator. And then when you press trace, and the closer you get to 3, you see that as x is getting closer to 3, y is getting closer to 6. So the limit as x approaches 3 should have been 6. And if you decided to do the table, hopefully you did the table anyway, you would have gotten these values. Now, you don't necessarily have to use 2.9, 2.99, so on and so forth. You could have used 2.7, 2.8, 2.9, but the only issue is that you're trying to figure out what's happening as x gets really close to 3. So you want to pick values that are really close to 3. And if you notice, when you actually plugged in 3, you would have gotten an error message, okay? And that error message basically means that, think about it, plug in 3 in here. 3 will give you 0 in the denominator. You cannot have 0 in the denominator. So that's why sometimes actually plugging in the value that is approaching won't give you the actual limit. It might just give you an error message, okay? Now, you can also find out these values by pressing second window and going to your table setup. Now, if you go down and highlight Ask on your independent section, then it will allow you, when you press second graph, it'll take you to a table where you can actually plug in these values and see them yourself. So if I actually type in 2.9 and enter, it's going to give me the value I would get if I actually plugged it into the equation. That's another feature. And yes, you can use it. Yes, you can use it. Now, one-sided limits are when you look at the values of y as x approaches c from each side. The negative is basically when you're approaching the function from the left, or the value from the left. And then the plus is when you approach the value from the right. And it's going to equal some y value. Now, a limitable function f of x as it approaches c exists if and only if both one-sided limits exist and if they're equal. So that basically means that if you're approaching c from the left and c from the right, they should equal the same value. Because if they do, then you know the limit as x approaches c, doesn't matter from the left or the right, is that value. These two things should equal each other. But if they don't, if they approach two different values, then you know that the limit as x approaches c does not exist. We talked about this a lot with your piecewise functions. So we're going to evaluate the one-sided limits here, and then we're going to see if they actually exist. So we'll look at both of these together. We're going to go to our y equals, and we're going to type in the absolute value of 2x over x. Now, absolute value is located when you press the math button, which is right underneath alpha, go over to number, there's ABS. Now, if you're lucky like me and it pops the absolute value bars, then you're good. But if it doesn't, you're going to have to close off your parentheses. So we're going to type in a 2x, go outside the absolute value bars, or put in the closed parenthesis and divide it by x, and look at the graph. Now, if you do not have this feature, then you're actually going to have to make a table of values and get a sketch of your graph, which we'll have to do for number 2. So if you notice, as x is approaching 0 from the left-hand side, my y values are staying consistently at -2. So the limit as x approaches 0 from the left is going to be -2. Well, if we look at it as it's approaching from the right, it actually approaches +2. And so since these two limits are not the same, the limit as x approaches 0 does not exist. Because in order to exist, as I said on the previous slide, it has to approach the same number. Let's look at this one. This right here is an example of a piecewise function.
Challenge members need to.
This is an example of a piecewise function which we talked about back in lesson 6. Do a quick sketch. G of x equals 4 is a line, a horizontal line that crosses the y-axis at 4. And since it says where if x is not equal to 3, that means at 3 you have a hole there. So this is what g of x equals 4 looks like. But then g of -2 actually is going to be a point at 3. Because technically it would have been a line at -2, but since it only said for x equals 3, then it's actually just in that one location. So now let's take a look. As we approach, we need to make a change real quick. All these should be +3s here. Make that change. All these should be +3s here. As we're approaching 3, from the left-hand side, my y value is 4. As we approach 3, from the left-hand side, it is 4. So then that means the limit as x approaches 3 in general is just 4, because they're equal. That is a big difference from saying the limit as x equals 3 of the function. Because if it equals 3, we're trying to figure out what is the value at 3. Well, here, it's not defined because there's a hole, but it's actually defined here. So the limit as x equals 3 is -2. Big difference. Big difference, especially with your piecewise function. So be very careful. If When it's talking about as x approaches with the arrow, that means it's looking from either side of that x value, not at that x value. So what I want you to do is I want you to find the limit of the next couple of examples. Look at the graph or use the table to try to figure out if your limit, what your limit is if it exists. Okay? And actually, I'll do this first one with you. I'm going to look at the graph because I have the option. If you don't have this option, make a table. So it's x minus 4 squared. I missed my x. I'm not going to clear everything out. I'm just going to press second delete. That allows me to insert in whatever I missed. Second delete. It allows you to insert in whatever you might have missed or if you made a mistake anywhere. So when I graph this, I'm trying to figure out what's happening as x is really close to 4. Well, I can kind of figure that this side is going to keep going up, 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 and up. So it's probably approaching infinity from the left-hand side. From the right-hand side, and again, I'm coming from the right to 4, tracing along the graph, it's getting really, really big, approaching infinity. So I believe my limit as x approaches 4 of this function is infinity. I'm going to verify it plugging in some values. So I'm going to go to second table. I'm going to cheat a little bit because I do have that option. I'm trying to get close to 4. So I'm going to type in 3.9, 3.99, 3.999. Oh yeah, that 1e to the 6 is basically 1 and 6 zeros. So that's 100,000. It's getting really big. Let me approach from the other side. 4.001, 4.01. Yeah, really, really big values. What's happening at 4? Of course I'm going to get an error message because it's not defined at 4. I would have 0 in the denominator if it was. But my limit as x approaches 4 from either the left or the right are both infinity. So that's my answer. Pause this video, find the limits for these, and then we'll check back in. Now hopefully you didn't get too thrown off because if you notice for B, the limit as x approached 0 of 1 over x, one approached positive infinity, one approached negative infinity, so yeah, the limit did not exist for B. For C, it did the same thing. It did the exact same thing. It approached positive infinity, approached negative infinity, which means the limit, again, did not exist. However, for D, both sides of the graph are going down to negative infinity, so that answer was negative infinity. And E, hopefully, you realize that you were dealing with a trig function, which means you need to be in radian mode. It just oscillated between -1 and 1. And if you recall from lesson 7, and then some of the ones from trig, when we actually looked at the graphs of trig functions, that if it's going back and forth between a value, it does not exist. So, in general, to sum all this up, if the limit as x approaches c does not exist if you have these three things that are happening. If f of x approaches different values from the left hand and the right hand side, if it increases or decreases without bound from the left and or the right of c, in other words, one approaches positive infinity, one approaches negative infinity, they have to approach the same value, and then also if it oscillates in between two fixed values like it did for cosine. That's when the limit is not going to exist. Otherwise, it's going to be either infinity, negative infinity, or a value. Okay? These limits at infinity. Okay? If the limit as x approaches c from the left is positive or negative infinity, or if the limit approaches c from the right is positive or negative infinity, that can happen. Okay? I don't want you to think that it doesn't happen, because clearly it does. Actually, now that I think about it, this slide should have been in between. It should have been before that last slide. But it's okay. We don't make mistakes. And if you notice, you could also have limits as x approaches infinity from the left or from the right. In those cases, you are going to approach a fixed value. So don't think that you can approach these values when you actually can. Okay? So here's some more that we're going to look at. Okay? This time we're looking at x approaches infinity. So now it's no longer one particular value. We're looking as x gets really, really big. So we're going to do this one together. We're going to look at 1 over x. So I'm going to graph it, zoom 6, look at my standard window. And I'm looking at the x values as x gets really, really big. So that means as x approaches 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It looks like it's going to be 0, but let me check with the table of values. Now I want to look at them as x gets really big. So I'm going to type in 100. That's just a pretty big number. That's 0.01. Let's do 1,000. Let's do 10,000. I notice that all of my values are getting really, really, really close to 0, because this 1 point e to the -4 just means you're going to be moving the decimal place to the left 4 spots and 5 spots, basically making it a number that's really, really, really close to 0. So the limit as x approaches infinity of 1 over x is equal to 0. Okay? And if you recall from that previous slide, if it approaches negative infinity or positive infinity, it's going to either approach a number or it's not going to exist at all. So, or actually, it could approach positive infinity or negative infinity. So now let's take a look at, I want you to look at the next two, pause the video, and then press play when you're ready to see what the answers are. Did you guys get this? I hope so. You should have seen that the graph as x got closer to negative infinity, it approached 2. And this one, sine x, it just oscillates in between -1 and +1. And since it doesn't approach one specific value, as x gets really big, the limit does not exist. This can even be applied to word problems. And guys, I don't want you to freak out because there's a word problem. Just read it. And I promise you, a lot of times it's a lot easier than the ones that I ask you to do that don't have as many words. So if a low energy swing door uses a spring to close the door and a hydraulic mechanism to dampen or slow down the door's movement. If the door is opened to an angle of pi over 4 and then released from its resting position, the angle of theta of the door t seconds after its release is given by an equation. We're actually given an equation here, which means that, hey, I have something that I can plug into my calculator, or I can plug in values to determine, okay? And yes, I know that says 1 equals 2t. That is a mistake, okay? That should actually be, excuse me, that actually should be a plus. So please make that change. It should be a plus 2t. We're going to estimate the limit as t approaches infinity of the function if it exists, and then we're going to interpret our result. We're going to actually say in words what this actually means. So we're going to plug this in. I'm going to make sure that 1, I'm in radian mode, which I am, and I want to be in radian because I am dealing with a trig function here. So I need pi over 4, and then I need 1 plus 2t. I can't get t, so I'm going to put an x, e, second ln, of -2t. Now, if you do not have a graphing calculator, you are going to have to make the table of values here, and then you'll just have to plug in really, really big numbers for t. Now I'm going to look at my graph. Okay? There's my graph. Now, if you want to be realistic about this, t in this problem represented seconds, which means that x in this graph represents seconds. I cannot have negative time. So I'm going to go to my window and change my window. I'm going to make my x-min 0, because again, I can't have a negative time. And actually, I kind of want to look at it a little bit bigger, because I'm trying to see what's happening as x gets really, as it approaches infinity. So I'm going to go up to 1,000. My y min, y max, I can leave there. Now let's look at our graph. So there it is. There's a graph of my function. I'm trying to figure out what's happening as x gets really, really big. I can click trace, and I can take a look. Okay, wow. Already at 500, I'm at 0. And the bigger I get, it's still at 0. So my limit does exist. It's just going to end up being 0. Okay? I can do a table of values too. And I still have those really, really big values from before. And they all show 0 as well. So the limit as t approaches infinity of my function is equal to 0. And what does that mean? Well, if time is t, and it represents basically the time it takes for a door to close, this is basically telling us that at some point in time, the door is going to end up being closed. It's not going to be open anymore. So this basically represents that as as time increases, the door comes closer to closing. That's basically what this represents, okay? Now, if you notice from our graph, at some point in time, the door was actually open, okay? Let me make my window a little bit smaller so you can see it. Let's go to 5, okay? Yep, it's looking like the door probably closed somewhere between 1 second and 2 seconds because that's when it hit 0, okay? So basically, at some point in time, the door was open, and the function basically represents the amount of angle that the door is before it actually closes. So that's all we had to do to represent this and interpret this. And so you guys realize that these word problems aren't too challenging. You just gotta read for one, and then go from there. So hopefully you guys will be able to do your homework. Make sure you bring your questions next week.